Okay, now we're recording. All right. So, what did we say? We said a sequence converges what if the elements, if the list, as we go out in the list, we get closer and closer to a particular value. In fact, it will get as close as you want. You can pick any degree of closeness, and the sequence will eventually get within that degree of closeness of the limiting value. Okay? And so that's the idea. You're honing in on a particular value, always getting closer to that value. Anything else for a sequence was divergence. So what does it mean for a series to converge? All right, well, what is a series? A series is a sum, right? You sum up all the terms of the sequence. So if you sum up all those terms and you get a finite value when you sum up all the terms of the sequence, then we say that that series converges. So again, we know the series means add up all the terms of the sequence, make a giant sum. If that giant sum equals a finite value, then that means that the series converges. Okay, so let's practice this. And again, this is a part of your quiz, or is your quiz tonight, is given expressions, can you identify, is it a sequence, is it a series, is it a sequence of partial sums, is it a partial sum, etc. So let's try this. So what is this expression? Is this a sequence, a series, a sequence of partial sums, a single partial sum? What is this?
A sequence.
He wants a sequence. The rest of you agree with that?
I agree.
Good. Yeah, that's a sequence. And so we want to write out that sequence like a third grader or second grader would understand. Write out the series like a second grader would understand. Write out the sequence of partial sums like a second grader would understand. So what would those three things be? Could you do it? So the sequence, the list. Sequence is the list. How do we generate the list? By letting I take on the values, what? From 1 to infinity. And so when you put in 1, what do you get?
3/2.
3 halves. That's the first number in the list. Put in 2. 12. Is that 6? 12 halves?
I got 12 fifths.
5.
Oh, 2, right. 12 fifths. What am I thinking? Okay, sorry. All right, and then?
27/10.
27/10, etc., right? On and on and on. So that's the sequence in explicit form, right? Writing out the terms. The series would be? Add them up. Okay, the sequence of partial sums would be another list. What's the first term in the sequence of partial sums? The first partial sum. The first partial sum is the sum of the first 1 terms. The second partial sum is the sum of the first 2 terms. The third partial sum is the sum of the first 3. And that makes a new list, right? That makes a new list. Okay. So, does the sequence converge? If so, to what value? Does the sequence converge? You're experts at this now, right? You're experts. So
Yes.
what kind of, we got a rational function. Does this converge or not?
Yeah.
Okay. Someone said it converges to 3. Agree with that?
Yes.
What does that mean? That means that as the I values get bigger and bigger and bigger and bigger, these terms get closer and closer and closer to 3. and as close as you want. Pick any degree of closeness, and you'll reach some I out there that will get this thing within that closeness of 3. So I'm going to write that like this. So like dot, 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 meaning we're going to go way out to the millionth term, the trillionth term, the quadrillionth term. What will these numbers in the list essentially be like? Starting at the millionth or the billionth term. What will these terms of the sequence be like?
Basically 3.
Basically 3, exactly. Essentially 3. For practical purposes, 3. Now, technically, no, not 3. But super, super close to 3 and always getting closer still. So I'm going to write that like this. The parentheses mean technically not 3, but for practical purposes, it's just going to be a list of 3s at the end. You're going to get so close to 3 that you can't tell the difference, and then they're just going to keep getting even closer than that. Okay? So yes, it converges to 3, and we can kind of write that and imagine that this way. Does that make sense? Does the series converge? So our series does the same. Series is just adding up all the terms of the list. So what do we say? The series converges if we get a finite value. What do you think? Are we going to get a finite value when we add all infinitely many terms of the list together? Is it going to be finite? No, of course not. Because why? In the end, what are we doing? We just keep... Yeah, we're just going to keep adding numbers that are essentially 3 forever. So that's just going to keep going up by 3. So this can't sum up to a finite value. How does the sequence of partial sums relate to the infinite series? We asked this question before. We never really answered it fully. Now it's time to answer it. So what is the sequence of partial sums? Every time we take the next term in the sequence of partial sums, we add on one more term of the series. So what happens when you get way, way out in the sequence of partial sums? So you're adding together the first, what? Million terms, then the first billion terms. So how does the sequence of partial sums relate to the infinite series?
The infinite series is I want to say it's a rate of change for the partial sums, kind of, because you're adding the next term on.
Okay. So the next term is so every time you add the next term, that's kind of like the rate of change a little bit, because it's how much you add on. But remember, the sequence of partial sums is every one of these is a partial sum. So like the first 3 terms, then the first 4, the first 5. So how can we set up a relationship between the sequence of partial sums and the infinite series? That list, what's the list that keeps adding one more term on? So isn't the sequence kind of like trying to become like the series? With every term that you go on to the next term, it's trying to be like the series, right? Does that make sense? And so when does the sequence actually become the series?
Near the very end.
Yeah, what's the end? What's the very end? I doing what?
Approaching to infinity.
Yeah, so if you can imagine I just getting infinitely big, then it's like if this were possible, if we could have the infinite partial sum, right? The infinite partial sum, like the last, if there was a last one, that would be the sum of the series. And so what is that? When you say like the infinite partial sum, or where the sequence is going in the end, what is that? What is that concept?
The limit.
Yeah, that's the limit. That's what you were doing in your homework. You're doing the limit. You were evaluating limits of sequences. So if I took the limit as I goes to infinity, can everyone still see that? Is that too low on my screen? Can you still see what I'm writing?
Yeah, I can see it.
Okay, so if you take the limit of the sequence of partial sums, that's capital S. So let's let SC. If I was able to get to get the limit of the sequence of partial sums, what would that be the same as?
The series.
That'd be the same as adding up all the terms, right? If you take this sequence out to the end, if you get this sequence all the way out to the end, then it's the limit of that would be the whole series. It'd be adding all of the terms together. Someone had a question?
Yeah, sorry, my Zoom ribbon is cutting off like
Okay, that's
little bit
that's
of
why I asked.
Yeah, I was gonna say that.
Press the Alt key.
Oh, oh, yeah, thank you.
Oh, does that help?
Yeah,
I'll just write it
the
again
Alt
up
key
here.
does help. It
So
gets
the
rid of-
limit as I gets big of the limits of partial sums equals the series. Super important. Super important. The value of the series, the value of adding up all the terms, is the same as the limit of the sequence of partial sums. If you were able to take the sequence of partial sums out to the end, you'd get the series. Because you'd be adding all the terms together. Does it make sense? It should make sense.
Can you say that one more time, like the overall concept?
Okay, tell me what you understand, because it should make sense, right? It's not like about the words that I say, but what's the concept here? With a sequence, we keep adding on one more term. So when will we get all the terms? Which term of the sequence will get all the terms added together?
Is that like infinity?
Yeah, like the limit, right? The limit at the end. So it's like if you take it to take the sequence to its end, that's equivalent to adding up all the terms of the series. So that's what we're saying.
Okay.
The limit of the sequence of partial sums is the same as the series.
Okay.
It should
Got
make
it.
sense, right? So it should make sense, not about kind of like, what were the words that he said? You know. All right.
I'm sorry, just quickly, is that because they both never end, really? They both go into infinity?
No. It's well, yeah. So. Yeah. So the series is adding up all the terms. Adding up all the terms. And so the sequence of partial sums, you keep adding one more on. So if you just kept going and going and going, kind of at the end of that, you'd be adding all the terms together. So if you really think about what the series is, and you really think about what the sequence of partial sums is, then it should make sense that when you get to these if you were able to get to the end of the sequence of partial sums, you'd be adding all the terms of the series together. Well, that's what the series is.
Okay, thanks.
Sure. Okay, so let's look at this one. I need to watch. Something tells me the time. What is the time right now?
10:10.
Thank you. 20 minutes. 10:10. Okay, so here we go. So what about this one? Oh, I'm sorry. So we said the series, that last series, CI, we said that diverges. It didn't converge, right? Because we just kept adding 3 over and over again. The limit of the sequence was 3. And so we saw that if you tried to add all those terms up, you just keep adding 3, 3, 3, 3, 3. So that diverges. Okay? And therefore, the limit of the sequence of partial sums that diverges also. They're the same, right? The limit of the sequence of partial sums is the same as the series. That first example diverges. Okay, this one. What is our series? So the series is 4/3, 4/6, 4/11. Am I doing the math right? 4/18, etc. Okay, the series would be, and so what about this one? What about the limit of this one?
Approaching 0.
Yep, so here, this one is another rational function. Degree of the denominator is bigger. Okay, and so this will do this. So when you get out to the millionth or the billionth or the trillionth term, you'll be essentially 0. Not technically 0, not exactly 0, but so close to 0 that for practical purposes it's the same, and then even getting still closer than that. Infinitely. Okay, so then the series what does that equal? That equals 4/3 plus 4/6 plus 4/11 plus 4/18 plus what? When we get way out there, say to the millionth term, million in first term, million in second term, and keep going. Okay, so our sequence converges to 0. What about the series? Converge or diverge?
Does it also converge?
Okay, and why does this one converge when the last one didn't? The last one converged.
Because
Yeah, go ahead.
we're practically adding 0 once we get to a value.
Right. So now our sequence is converging to 0. That means the terms are getting infinitely close to 0. So then in the end, we're adding such a minuscule amount each time that the whole sum has a can sum up to a value. Okay? And so what is the value of the series? How can I figure out what does that equal to when I add it all up?
Could you take the limit of the sequence of partial sums?
Very good, very good. Right, so this we said last time, the series equals the limit of the sequence of partial sums. I'll call that SDI. So the sequence of partial sums for sequence D. Okay, so that's true. But what's that, right? What's that? So let's take a look. I've got a GC file to kind of analyze all this and figure out what's going on here. So now we think that this one's going to converge because eventually, since the sequence converges to 0, in the end we're just adding on values that are so small that this thing will add up to a finite value, rather than just going off. In the previous one we just added 3 every time. So let's take a look at that. Okay, so here are those two sequences using J instead of I. So here on the y-axis is going to be the value of the partial sums. And then this is the value of I. Okay, so when I was 1, we got, what do we get? 3 halves. And so here's I1, we got 3 halves. All right, and then when I was 2, we got the sum of the first 2 terms. So the partial sums would be the sum of the first 2 terms of this one. And that would be like this. So here's I equals 2, and then the second partial sum, which is the sum of the first 2 terms of the sequence. Right? And then continuing on like that, these are the partial sums. And the sequence converges to 3. So then eventually, what's happening? We're just, to get the next partial sum, it's eventually, essentially just adding 3 each time. So that sequence of partial sums just keeps growing and growing and growing, and eventually growing by 3 every time. So does that make sense with that first sequence that we did? The limit of the sequence was 3, so the partial sums keep growing by 3 each time because you keep adding another, or essentially 3, right? Essentially 3 in the end. And so then that sequence of partial sums just keeps getting bigger and bigger and bigger, and so that series will just never stop. It'll be infinitely large, right? There'll be no bound to the sum of all the terms because they keep growing. It keeps going by 3 every time you go to the next term. All right, what about this other one? What was the limit of that sequence?
0.
0. So what's going to happen with those partial sums? We're going to keep adding a smaller and smaller value on each time. So here I am at I equals 27. And you see that the amount by which the partial sum increases is getting smaller and smaller, and we know that will just, the limit of that sequence was 0. So in the sequence of partial sums, you keep adding on essentially 0 plus 0 plus 0, and so that's why the total sum has a chance to converge. So the question was, what did that series converge to? So we were looking at this series here. How can we, if we don't know what it is exactly, how can we get a good idea? So we say this converges, but to what? So what could give me an idea of what it converges to, or maybe like an approximation?
Find the value on this graph for like when I is a really, really big number.
Okay, so the biggest one I've got here is I have I equals 29 here. So I'm showing I equals 29. So when I equals 29, I want the value of what at I equals 29?
The partial sum.
The partial sum, right? If I took the 29th partial sum, that would give me some kind of estimate of the whole sum, right? And you can right, you see this leveling off. So all these partial sums are giving me estimates of the whole sum. Huge point. A partial sum is an approximation of the whole sum. So if you're
Is
ever
that true? Sorry.
if the series converges. If the series converges, right? So that wouldn't make sense to say it about this one. Any partial sum you picked here would be a finite value, and we know this sum just keeps growing and growing and growing. So when the series converges, a partial sum, it could be an approximation of the whole sum. And then which partial sums are the best approximations? Or what partial sum is a better approximation?
The larger, the better.
Right, the further down in the list, right? So for greater values of I, the greater your value of I is, the better the approximation is because you have more terms included from the series. So as I increases, the partial sums become better and better approximations of the whole sum. So Go ahead.
How can we tell when the series starts to converge? Well, the partial sum starts to converge to one certain point.
Well, you have to either look at the graph or look at the numbers. It's always converging. It's always getting closer.
Yeah.
But it's just about to your level of satisfaction, right? So is this a good enough approximation for you? So maybe for someone, oh, this is a good enough approximation. someone says, no, I need a better approximation. So this is a good enough one for me. So it's
Is
just
there a way to do it without the graph?
looking at the numbers. So I got a table here.
Oh.
So here's the table. Here's the table of partial sums for that one. And so down here at the, I actually have 300th is this. I don't know if you can read that. I can barely read it. What does it say?
3.4308.
08. That's at I equals 300. This is I equals 400. I equals 400. The partial sum is 3.43412. Do I have that right?
Yeah.
And then I put in 3,000. And I got 3.44278.
Yeah.
So what happens is, as I keeps increasing, you'll lock in decimal places. So like by the time we got to I equals 300, pretty much this was locked in. This decimal place was locked, 3.4. And then notice that when we went from 400 to 3,000, it went up a little bit more to get that probably locked in to the 100th place. Will it ever reach 3.45? Don't know. Don't think so, but maybe, right? But so there'll come a point when each decimal place gets locked, and we're only messing with smaller and smaller decimal places, right? But I could come in here and I could graph the line. Y equals 3.44, say 3. So we're thinking maybe the whole sum of the series is going to be pretty close to 3.443, something like that. And so there we see the partial sums giving better and better approximations to the value of the whole sum, or the entire infinite series.
Is it possible to find this value without like GC or something?
So certain series have ways, certain series have techniques for finding the actual value. So they're, but for our purposes, like one like this, we're not going to have a formula or a way to get this series exactly. So the best we can do is take a really, really long partial sum, right, with a lot of terms, and call it a day. We say, well, it's going to be pretty close to 3.443. And so some series, there is a way algebraically, a formula to give you the whole sum. And we're supposed to see that today. I don't know if we'll get to it. Other series, you can't, like this one, without some more advanced techniques, we're only stuck with approximations from partial sums. Does that answer it?
Yes, thank you.
Okay. Other questions? All right, so let's keep going here. Let's look at 6 minutes. So here's something called the divergence theorem. So what happened? When the sequence didn't go to 0, what about the sum of the series?
It diverges.
Yeah, right? Because the sequence, remember the first sequence? It went to 3. So if you try to add up all the terms, you end up just adding an infinite number of essentially 3's. Well, that's never going to sum up to a finite number. When was it that we got the series to converge?
When it was 0.
When the sequence converged to 0, so that when you're adding them all together, then you're adding on a smaller and smaller number, and then essentially 0, and then it could level off, right? So the divergence theorem says that a series will diverge if the sequence does not converge to 0. That should make sense. The only way that a series could converge is if those terms in that sequence get really, really small to 0, because you're going to keep adding on forever values. The only way that can converge is if those values eventually become 0. Super important. So this is what we're saying. This will always be the first thing to check when analyzing a series. If your sequence does not converge to 0, game over. You can stop. No more to be talked about. The series could never converge.
What about a series that goes, like we saw last time, -1, 0, 1, 0, -1? Wouldn't that would diverge, but wouldn't the series converge at 0?
No, it doesn't converge because what is it? So then the sequence of partial sums, so like you're going to go on and on like that. So what's the sequence of partial sums? -1, -1, 0, 0, -1, -1. Here's the sequence of partial sums. There will always be -1s and 0s in that sequence of partial sums. That does not converge. Therefore, the series does not add up to a value.
Gotcha.
Does it make sense?
Yeah.
Okay. All right, again, if this sequence doesn't converge to 0, the series could never converge. And we saw that with the 2 examples. We saw that with the example of the sequence going to 3 and the series just blowing up, right? Because you keep adding 3 over and over again. Okay, so now that being said, let's look at something called the harmonic series. What about this? Harmonic series. So what is that? That's an infinite series, I to 1 to infinity. 1 over j, as a second grader would understand, these symbols would be what? As a second grader would understand those symbols, what would it be?
Series.
No, that's not how a second grader understands this.
Second grader would be like, oh, 1 over 1 plus 1 over 2
right.
plus 1 over 3.
They would understand this, right? If they understood fractions. That's what this means, right? We see this, think this, always. See this, as a calculus student, think this. Right? That's what that means. Okay. Let's bring that back. Okay. Okay, so there it is. And what about this sequence? Does the sequence converge? 1 over I to the j, does the sequence converge?
Eventually to 0, yes.
Okay.
It's at a slower rate than the previous one.
All right, so does it converge, yes or no?
The sequence would converge.
Yeah. So, converges to 0. Converges to 0, right? So, why? Because the denominator just gets big, right? And this is a p sequence, right? P sequence with p equal to what?
1. P equals to 1.
P equals 1, greater than 0, converges, right? That's our p sequence with p equals 1, greater than 0. All right, so let's analyze the series now. So we're going to add them all up. And so what do we think? Series will converge because the sequence converges to 0. Yes, yes. Okay. So here we go. I'm going to compare this to this sequence. So 1 over 1, 1 over 2, but instead of 1/3 plus 1/4, on this new sequence I'm writing down, I'm going to do 1/4 plus 1/4, which equals what?
A half.
A half. And then instead of the next 4 terms, I'm going to write 4 1/8, which also equals a half. And then instead of the next 8 terms, I'm going to add all 1/16 together. Okay, can I ever stop? Will I ever be able to not do this? I'll never run out of terms, right? So I can always double the number of terms in this one and get a half, right? So I can do 16 1/32, and that will equal a half. And then I can do 32 1/64, and that equal a half. How does this compare to a half? Bigger or smaller? 1/3 plus a fourth.
Bigger.
It's bigger, right? And how does this sum compare to the sum of 1/2 of 4 1/8?
Also bigger.
Bigger. How about this?
Also bigger.
Right. So if I keep doubling the number of terms that I add together, I always get something that's bigger than a half, comparing it to this other sequence that I formed, the series. So what about the harmonic series? I can always take twice as many terms, and the sum of that partial sum will be bigger than a half. And I'll always be able to take twice as many because this is an infinite sum. Conclusion?
It diverges.
This diverges. But I thought it was supposed to converge because the series, the sequence converged to 0.
We basically said that it will never converge if it doesn't go to 0, but we never said that it must converge if it is 0.
Yeah, well said. Did you hear that? We said that if this doesn't converge to 0, then the series diverges. We know that for sure. But we never said, like she said, we never said that if this goes to 0, it guarantees that it converges. And this is proof that it doesn't. So if the sequence converges to 0, what's the conclusion?
It might converge.
Depending on the sequence. Depending on the sequence. Some sequences that converge to 0 result in a sum that converges. That was like the first example we saw. 4 over I squared plus 2. Some sequences that converge to 0 end up in a sum that diverges, like the harmonic series. Right? This still converges to 0. So what's the problem? This is not converging fast enough to 0. So let me show that in the graph and we'll be done. How far over am I? Just 3 minutes. Okay, so I have that one too. So here was the first one. This sequence converged to 3, and so the series just blew up. This sequence converged to 0, and we said that it also the series converged. So then the harmonic series looks like this. The black one is the harmonic series. The sequence converges to 0, but notice these are still getting bigger. This will not level off, ever. It will keep getting as big as you want, as long as you take enough terms. It's kind of like the square root of x. It will keep getting bigger and bigger and bigger. It will not level off, whereas the red one did. So it sure looks like it's going to level off, but it doesn't. Pick any value of a partial sum here and take I far enough out, and this sequence will get that high. It's not going to level off. It'll just keep growing eventually for big enough I. Okay.